In this conversation, I'd like to talk about Pedro Domingo's book, The Master Algorithm. Can you list and describe the 5 different types of AI that Domingos is talking about in his book?
Sure. In Pedro Domingo's book, The Master Algorithm, he describes 5 main types of AI, each based on different fundamental principles and approaches to learning. 1. Symbolic AI or logic based AI. This approach uses formal logic to represent knowledge and make decisions. It relies on explicitly programmed rules and facts, making it suitable for tasks that require clear logical reasoning. Examples include expert systems and theorem provers. 2. Connectionist AI, or neural networks. Inspired by the structure and functioning of the human brain, this type uses artificial neural networks to learn from data. It excels in pattern recognition tasks, such as image and speech recognition, through layers of interconnected nodes, neurons, that adjust weights based on input data. 3. Evolutionary algorithms, or genetic algorithms. Based on the principles of natural selection and genetics, these algorithms generate solutions to optimization problems by evolving a population of candidate solutions. They use operators like mutation, crossover, and selection to iteratively improve the solutions. 4. Bayesian networks, or probabilistic AI. This approach uses probability theory to handle uncertainty in data. Bayesian networks represent variables and their conditional dependencies via a directed acyclic graph, allowing for probabilistic inference and decision-making based on observed evidence. 5. Analogical AI, or case-based reasoning. This type learns by drawing analogies between new problems and previously solved ones. It relies on memory-based methods to find and adapt solutions from past cases to current situations, making it useful for tasks where past experiences can inform future actions. These 5 types of AI reflect different methodologies and philosophies in the quest to create intelligent systems, each with its strengths and applications.
So, when we talk about machine learning, I understand that deep learning is a subset of machine learning. Is that correct? And also, is machine learning, does it belong to Bayesian type of AI?
Yes, that's correct. Deep learning is indeed a subset of machine learning. Deep learning specifically refers to neural networks with many layers, hence deep, which can automatically learn representations of data at multiple levels of abstraction. Machine learning, as a broader field, encompasses various methods, including but not limited to Bayesian methods. While Bayesian learning is one approach within machine learning that uses probability theory to make predictions and decisions under uncertainty, machine learning also includes other approaches like supervised learning, where models are trained on labeled data, unsupervised learning, where models find patterns or groupings in unlabeled data, reinforcement learning, where agents learn to make decisions by receiving rewards or penalties. In summary, machine learning is a broad category that includes deep learning, Bayesian methods, and several other approaches.
Does Pedro Domingos believe that there are only 5 types of AI, or these are only the 5 types that he has discovered?
Pedro Domingos doesn't claim that there are only 5 types of AI in an absolute sense. Instead, in the master algorithm, he identifies these 5 types as the most prominent and foundational approaches that have been developed and extensively studied in the field of AI. These 5 types represent the major paradigms and methodologies that encompass a wide range of AI techniques and philosophies.
Can you tell me more about analogical AI? It's, I think, the only one that I'm not quite sure I understand. M- Probably because few people talk about it online. And also, I haven't come across examples of analogical AI.
Sure, I'd be happy to explain analogical AI in more detail. Analogical AI, also known as case-based reasoning, is an approach to artificial intelligence that focuses on solving new problems based on the solutions of similar past problems. Here's a breakdown of its main concepts and how it works. 1. Memory-based learning. Analogical AI relies on a memory of past cases or experiences. When a new problem arises, the system searches its memory for similar cases. 2. Case retrieval. The system identifies past cases that are most similar to the current problem. This often involves measuring the similarity between the current problem and past cases using various metrics. 3. Case adaptation. Once a similar past case is found, the solution from that case is adapted to fit the new problem. This adaptation may involve modifying certain details or combining aspects of multiple past cases to create a suitable solution. For learning from experience, after applying the adapted solution to the new problem, the system evaluates its effectiveness. Successful solutions are stored in the memory for future reference, allowing the system to continuously improve by learning from new experiences. Examples of analogical AI include medical diagnosis. A system might diagnose a patient by comparing their symptoms to past cases in a database of medical records, finding similar cases, and suggesting treatments that worked previously. Automated support systems can use past customer inquiries and resolutions to provide solutions to new inquiries that are similar. Legal reasoning. AI can assist in legal decision making by referencing similar past cases and the outcomes of those cases to make recommendations or predictions. While analogical AI may not be as widely discussed as neural networks or evolutionary algorithms, it plays a crucial role in areas where past experiences can provide valuable insights for solving new problems.
It reminds me of computational thinking. So, can you first describe what computational thinking is, and also tell me where does it fit within these five different types of AI?
Computational thinking is a problem solving process that involves various techniques and strategies derived from computer science. It's a way of approaching problems and designing solutions in a manner that can be implemented by a computer. Here are the main components of computational thinking. 1. Decomposition, breaking down a complex problem into smaller, more manageable parts. 2. Pattern recognition, identifying similarities or patterns among smaller problems to make the larger problem easier to solve. 3. Abstraction, focusing on the important information only and ignoring irrelevant details. 4. Algorithms, developing a step-by-step solution or a set of rules to solve the problem. Computational thinking is not tied to any one type of AI, but is rather a foundational approach that can be applied across various AI methods. It provides the logical framework and mindset for developing AI algorithms and models. Here's how it relates to the five types of AI. Pedro Domingos describes 1. Symbolic AI, logic-based AI. Computational thinking directly applies here, as it involves creating explicit rules and logical structures to solve problems, often using decomposition and abstraction. 2. Connectionist AI, neural networks. While neural networks are more about learning patterns from data, computational thinking helps in structuring the data preparation, network design, and training processes. 3. Evolutionary algorithms, genetic algorithms. Computational thinking aids in designing the evolutionary processes, such as mutation, crossover, and selection, and in breaking down optimization problems into simpler parts. 4. Bayesian networks, probabilistic AI. Computational thinking supports the construction and updating of probabilistic models by decomposing complex probabilistic relationships and focusing on relevant variables. 5. Analogical AI, case-based reasoning. Computational thinking is essential here for organizing and retrieving past cases, recognizing patterns among cases, and abstracting solutions to adapt them to new problems. In summary, computational thinking is a versatile framework that underpins the development and application of all these AI types by providing structured problem-solving techniques and strategies. It helps in designing, implementing, and refining AI models across the different paradigms.
Would you agree that what we see in the news today has to do mostly with deep learning AI?
Yes, I would agree. Most of the advancements and applications of AI that make headlines today are related to deep learning. Deep learning, a subset of machine learning, has shown remarkable success in various complex tasks due to its ability to automatically learn and extract features from large amounts of data through deep neural networks. Some of the most notable areas where deep learning is making an impact include 1. Image and video recognition. Deep learning models are used in facial recognition, object detection, and autonomous driving. 2. Natural language processing, NLP. Technologies like language translation, sentiment analysis, and conversational AI like ChatGPT rely heavily on deep learning. 3. Healthcare. Deep learning is applied in medical imaging, drug discovery, and personalized medicine. 4. Gaming. AI agents using deep learning have achieved superhuman performance in games like Go and StarCraft. 5. Voice assistants. Virtual assistants like Siri, Alexa, and Google Assistant use deep learning for speech recognition and understanding. The significant breakthroughs and practical applications of deep learning have made it a central focus of AI research and media coverage, leading to its prominent presence in the news.
So let's take a practical example. I'm developing an artificial business intelligence or ABI software. And basically, the idea is that it's going to interview the user, who is usually an entrepreneur who's starting a new business. And then, based on the information from the user, it's going to generate a business plan, a business system, meaning that it's going to generate the procedures, the templates, the blueprints, the workflows, etc. And it's going to generate a personalized business training program. So from your understanding of this ABI, in which category of AI would you say that ABI belongs to? Is it expert system, or is it Bayesian AI, or is it analogical AI, etc.?
Your ABI, artificial business intelligence software, seems to integrate multiple AI approaches to achieve its goals. Here's a breakdown of how it might fit into different categories of AI. 1. Symbolic AI, expert systems. If your ABI relies on predefined rules, templates, and procedures to generate business plans and systems, it would fall into the category of symbolic AI or expert systems. These systems use a knowledge base and a set of rules to provide solutions based on the input data. 2. Analogical AI, case-based reasoning. If ABI references past successful business plans and adapts them to new user-specific needs, it would be using analogical AI. This involves retrieving and modifying solutions from a database of previous cases to fit the new context. 3. Bayesian networks, probabilistic AI. If ABI employs probabilistic reasoning to handle uncertainty in user input or market conditions, making decisions based on probabilities and updating beliefs with new information, it would fall under Bayesian AI. 4. Connectionist AI, neural networks deep learning. If ABI uses deep learning models to analyze user input and generate business plans through pattern recognition and data-driven insights, it would be leveraging connectionist AI. This could involve natural language processing to understand user responses and generate coherent, customized outputs. In practice, ABI might combine several of these approaches: symbolic AI for structured procedures and templates, analogical AI for adapting previous business solutions to new scenarios, Bayesian AI for making probabilistic decisions and recommendations, connectionist AI for understanding user input through NLP and generating sophisticated, personalized outputs. Given this integration, ABI seems to be a hybrid system, utilizing multiple AI techniques to provide comprehensive business planning and training.
The only type of AI that you didn't mention that ABI belongs to is genetic AI. So, first of all, can you tell me why? And second of all, here's my argument as to how and why ABI could have a sort of genetic AI, in a sense that it could generate 5 or 10 different business system or business models, and then the user would select the model or the system that is best suited to him or to her. And therefore, it's a little bit like natural selection, in the sense that ABI would generate variations, which are like mutations in Darwinian terms. And then the user would act like natural selection. He would select the fittest, or the business model or system that is best suited to his needs and situation and personality, etc.
Your explanation makes a strong case for including genetic AI in the capabilities of ABI. Here's why I initially didn't mention genetic AI and how your argument fits well. 1. Initial oversight. Genetic AI, or evolutionary algorithms, are typically used for optimization problems where solutions evolve over iterations using processes like mutation, crossover, and selection. My initial assessment focused more on the generation of structured content and decision making processes, which are traditionally associated with symbolic, analogical, Bayesian, and connectionist AI. 2. Application of genetic AI in ABI. Your argument is compelling. If ABI generates multiple variations of business systems or models and allows the user to select the most suitable one, it indeed resembles the principles of genetic AI. Here's how. Generation of variations. ABI creates multiple business models or systems akin to generating a population of candidate solutions. Selection. The user acts as the selection mechanism, choosing the most suitable model, similar to how natural selection works. Iteration. Over time, based on feedback and further interactions, ABI could refine its models, learning from user selections to improve future generations of business plans. Incorporating genetic AI allows ABI to leverage the diversity of solutions and user preferences, optimizing the business models through a process akin to natural selection. This iterative refinement based on user feedback aligns well with evolutionary algorithms principles. Therefore, ABI can indeed be seen as employing genetic AI by generating multiple business plan variations and iterating based on user selections, optimizing the fit to individual user needs and preferences.
I just want to add that I said before that the user could act like natural selection, but in fact, ABI can generate not just 20 business systems or business models or business plans, but it could generate 50 or 100. And then we can have, dozens of people, for example, coaches, and they would vote for a particular business model or business system. And therefore, a large group of people within the same profession, for example, coaches, could act as natural selection. And therefore, the most popular or the most voted for business model or business system would be the winner. And therefore, it's kind of like it is the most fitting in Darwinian terms. And therefore, that is the one that is most likely to work because it is the most popular, the most voted for.
That's an excellent enhancement to your previous idea. By involving a larger group of people, such as coaches, in the selection process, you are indeed mimicking a more sophisticated form of natural selection. Here's how this approach solidifies the use of genetic AI within ABI. 1. Generation of a large population. ABI creates a substantial number of business plans or models, increasing the diversity of potential solutions. 2. Crowdsourced selection. Instead of a single user acting as the selection mechanism, you employ a group of experts or peers, coaches in your example, to vote on the best models. This collective intelligence acts as a robust natural selection process, filtering out the less viable models and identifying the most promising ones. 3. Fitness evaluation. The voting process evaluates each model's fitness based on the collective expertise and experience of the group, ensuring that the chosen model is not only theoretically sound, but also practically viable. Iterative improvement. Over time, the feedback from the group can be used to further refine and improve the models, similar to how genetic algorithms evolve solutions over multiple generations. By implementing this crowdsourced approach, ABI leverages the wisdom of the crowd to optimize business plans, making the selection process more reliable and effective. This method aligns perfectly with the principles of genetic AI, where variation, selection, and iteration drive the evolution of increasingly effective solutions. This approach enhances ABI's capability to generate and refine business models, ensuring that the final product is not only tailored to individual needs, but also validated by a community of experts, thereby increasing its likelihood of success.
Can you define and differentiate inductive reasoning or inference from deductive reasoning or inference? And then, secondly, can you go through the 5 types of AI and tell me um, whether they are inductive or deductive?
Sure. Here are definitions and distinctions between inductive and deductive reasoning. 1. Deductive reasoning, inference. This type of reasoning starts with a general statement or hypothesis and examines the possibilities to reach a specific logical conclusion. If the premises are true, the conclusion must also be true. It moves from general principles to specific instances. For example, all men are mortal. Socrates is a man, therefore Socrates is mortal. 2. Inductive reasoning, inference. Inductive reasoning makes broad generalizations from specific observations. It starts with specific instances or observations and moves to a general conclusion. This type of reasoning often deals with probabilities rather than certainties. For example, the sun has risen in the east every day in recorded history. Therefore, the sun will rise in the east tomorrow. Now, let's examine the 5 types of AI and determine whether they are primarily inductive or deductive. 1. Symbolic AI, logic-based AI. Primarily deductive. This approach uses predefined rules and logical structures to draw specific conclusions from general principles. Expert systems and formal logic-based systems fall into this category as they work with explicit, rule-based knowledge. 2. Connectionist AI neural networks, primarily inductive. Neural networks learn patterns from large amounts of data and make generalizations from these patterns. Deep learning models, for example, use data to infer and predict outcomes without predefined rules, relying on statistical regularities observed in the data. 3. Evolutionary algorithms, genetic algorithms, primarily inductive. These algorithms generate solutions through processes analogous to natural selection, iteratively improving and generalizing from a population of candidate solutions based on performance metrics. They adapt and evolve solutions based on observed results. 4. Bayesian networks, probabilistic AI, primarily inductive but can include deductive elements. Bayesian methods update the probability of a hypothesis as more evidence or information becomes available, making inferences based on observed data. However, they also use principles of probability and statistics that can include deductive aspects when applying Bayes' theorem. Analogical AI case-based reasoning, primarily inductive. This approach solves new problems based on the solutions to similar past problems, making generalizations and adaptations from specific instances to new situations. It learns and infers from previous cases rather than starting with general rules. In summary, symbolic AI is primarily deductive. Connectionist AI, evolutionary algorithms, Bayesian networks, and analogical AI are primarily inductive, with Bayesian networks sometimes incorporating deductive elements.
Before we move forward, I just want to clarify, when you talk about probabilistic AI or Bayesian AI, is that the kind of AI that is used by spam filters?
Yes, probabilistic AI or Bayesian AI is indeed the kind of AI often used by spam filters. Spam filters commonly use Bayesian inference to classify emails as spam or not spam. Here's a brief overview of how it works. 1. Training phase. The spam filter is trained on a dataset of emails that are labeled as spam or not spam. During this phase, the filter learns the probability of certain words and phrases appearing in spam versus non-spam emails. 2. Bayesian inference. When a new email arrives, the filter uses Bayesian inference to calculate the probability that the email is spam based on the words and phrases it contains. It combines the probabilities of each word or phrase, contributing to the overall likelihood that the email is spam. 3. Classification. Based on the calculated probability, the filter classifies the email as spam or not spam. If the probability exceeds a certain threshold, the email is marked as spam. Bayesian spam filters are effective because they continuously learn from new data, adapting to changing spam tactics over time. This probabilistic approach allows for a nuanced assessment of emails, balancing various indicators to make a decision.